So now in this video I thought we would take a quick look at a current regulating diode component there. So it's actually just a little component that was put on a board. I got this from a Joe Knows Electronic Semiconductor kit, which I get components for a number of my videos. So in any case, we're going to measure voltage. Power supply voltage right now is 7 volts. We're not going to need much current at the power supply where it won't let more than 5 milliamps of current flow. Just in case I mess something up, short circuit or something, we won't have damaging current. So in any case, this is a Zener diode, and this is going to limit the current that flows through it, and it's going to keep it pretty steady. So here's one of the uses for that. We know now with this Zener diode, it's going to maintain this reference voltage of 5.152 volts right there. I think I said that right, but in case you saw the number. So in any case, now we're going to we could probably bump it to 17, but I think 15 might be about the limit I want to keep it to. We'll look at why later. And now we'll zoom in. And so when you change the current that flows through a Zener diode, it will change its reference voltage slightly. And a lot more than what you see here though. We did not really change the current though. And there you can see the voltage is practically the exact same, even though we went from 7 volts to 15 volts. So what I'm going to do is set the meter to measure milliamps of current. So this is the S102, and the 102 means that it's going to let about 1 milliamp of current flow through it. So first, we can do with the Zener. Make sure that we're getting 1 milliamp of current when we have the Zener there. And so current you measure in series right there, and there you can see 0.88, and there you can see if I bypass the Zener diode, no current is going through the Zener diode. You can see that it is the same. If it helps, you can remove the Zener diode completely right there. I can take an LED, and we're going to get the same. So it's supposed to be 1 milliamp of current. Looks like it's falling a little bit shy right there. But the main takeaway, even as we change the load significantly, it is passing the same amount of current. 0.88 milliamps right there. That's with the power supply at 15 volts. Now let's go back down to 7. So it doesn't matter what the voltage is. It can be a wide range right there. It's setting the current. It's not dependent on voltage other than, you know, how hot it's going to get. Of course, higher voltages, it's going to get hotter. At some point, you might cause damage. We'll bypass them. And there you can see, we're getting a very steady 0.88 milliamps of current through this component, which, again, is useful for reference voltages. And now we'll take a look at the diagram I put together a long time ago for this. So this is the S102T. I got it from the Joe Knows Electronic Semiconductor kit. I don't really recommend you go out and just buy these individually unless you could really use them. But if you get that kit, you get a couple of them and a bunch of other cool components. So I got this information here. First we'll look at the basic circuit that I think might be most interesting. We're going to get that pretty stable reference voltage through the Zener diode right there, 5.1 volts. Of course, you could see it was slightly different, but the main thing was it held steady. We got a reference voltage that changed even if the supply voltage changed greatly right there. So we got the S102. It's on this board. Maybe we'll take a closer look at the component later on. But we got the positive side there going to what is called the anode. And then there's the cathode, which I'm pretty sure has a little gray band on the component. It's a little surface mount component, kind of hard to see. But in any case, it's put on a board, and then they got pins coming out of the board there to wire to the circuit. You can see we're using the top and the bottom one right there. And so yeah, that's going to let about 1 milliamp of current go through. We know that from the number there, and we measured it. We actually got 0.88 because it's not a perfect current source. But in any case, you know, it's about 1 milliamp of current. It holds steady though, so we'll get a steady Zener voltage. We should always have about 5.1 volts as long as current is coming from a higher voltage source. But it does vary a bit as current varies. So if you want a really steady voltage at this point, you want a steady current no matter what's happening with the supply. Hopefully that makes sense. So let's look at this a little bit more. The number lets you know the amount of current that is flowing through there. So 102. Think of it as 1, 0, and then 2 more zeros for 1,000. And I wrote a little more detail on why that is. And that 1,000 is in microamps. So 1,000 microamps is the same as 1 milliamp. Now, I must have looked at the data sheet a long time ago and came up with this. Usually, there's a tolerance. You know, it can be a percentage higher or lower for a lot of components unless they're precision. But yeah, this looks like you might end up with 0.88 milliamps using this component, or you might have 1.3 or anything in between. So yeah, it looks like this particular one's on the lower end. There's another one in the kit here. You know, I'm guessing it's probably a little bit higher since this is the absolute minimum, but it can be in that range as we saw there. And yeah, if that math doesn't quite make sense yet, you could also I guess there's a 301 component there, and so that's 30 and then another 0, so that would be 300 microamps, as you see right there, which is the same as 0.3 milliamps. So if you could use that current, you'd want to find that part number. And so I have the rated power. The E series, so leaded, has wires coming out of it like other components. Looks like it has a lower wattage rating than the S series, which we are using right here, the surface mount component that's put on a board. Looks like it has a higher wattage rating. So again, it's letting 1 milliamp of current go through, and so you multiply that by the voltage across the current regulating diode component. Hopefully that makes sense. And I must have had a good reason why I put this down, a good explanation, but I don't remember anymore. I put this diagram together a long time ago. But in any case, I think I covered everything that is on the diagram there. And finally, we will take a look at the component. So when it was on the board, we had the anode on top, cathode on the bottom. The middle pin I don't think is connected to anything. Let's get a closer look. So there is the solder pad right there for the middle one. Doesn't come up to anything, doesn't look like. That one doesn't look like it connects to anything, but obviously it does. And there we go. So here is the actual component. There we go. I turned it so we can see the number there. And so you see 102, as we said before, the S102. And you can tell there's a grayish band kind of over there on the right. So that is the cathode side. And the right, as we saw before, on the board was down towards the bottom, right there, connected to the Zener diode. So that's about all I got for this component. And again, I don't think, you know, you probably want to go out and buy a whole bunch of them just for fun, but the Joe Knows Electronics semiconductor kit has a lot of cool semiconductors, so I believe in buying the kit once you have your basic components. So in any case, thanks for watching this long. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.